In this video, I'm going to introduce you to the Little Man Computer simulator and show you how to write some simple programs using the Little Man Computer programming language. In later videos of this series, you'll see some more complicated Little Man Computer programs that include branching and looping. In 1965, Professor Stuart Madnick, an American-born computer scientist, wanted to demonstrate the von Neumann architecture to his students, so he created a simplified working model of a computer. He imagined that a computer running a program was similar to a little man sorting letters and parcels into pigeonholes in an old-fashioned mailroom, so he called his model the Little Man Computer. The model proved to be such a powerful learning tool that it's still used today to introduce computer architecture and low-level programming to students of computer science. Indeed, being able to write Little Man Computer programs is a skill required by some advanced-level computer science courses. Since 1965, lots of simulators have been created to demonstrate how components such as the CPU and the RAM work together while running an assembly language program. Some of these simulators are incredibly detailed models of specific types of CPU architecture, whereas others are much simpler and focus on features common to most processors. One of the most popular Little Man Computer simulators was created by Peter Higson, at the time a computer science lecturer at University College London, and it's this particular simulator which I'm going to talk about now. These days most programmers use high-level programming languages, which are very solution-orientated. Programmers can focus on what it is they're trying to achieve without concerning themselves too much with what's going on inside the computer. High-level languages are also similar to the way we speak, so they're relatively easy to learn. But in the early days of computers, programmers had to write code in low-level programming languages, known as assembly languages. An assembly language was referred to as a low-level programming language because the instructions were very explicit about how the data should move around inside the computer. The programmer had to think about the way the CPU and the RAM actually worked. Some programmers still write assembly language code today, when it's important to produce highly optimized code. Every type of central processing unit has its own assembly language. All of the possible commands that a particular processor can understand, or should I say, all of the operations that a processor can perform, are known as the processor's instruction set. When a programmer writes assembly code, they're limited to the instruction set of the processor that they're writing their program for. This is the instruction set of the Little Man Computer simulator. You may be surprised to see that there are only 11 operations in the instruction set. But, nevertheless, like any assembly language, it's possible to write thousands of different programs to perform thousands of different tasks, with only a handful of operations available. This program, for example, will allow the user to input two numbers and it will multiply them together. You may well be thinking, that's a lot of complicated looking code to perform such a simple task. Well, yes it is. This is how you would perform the same task in Visual Basic, and this is how you would do it in Python. But it's a feature of assembly languages that you have to write a lot more code to do the same job. Notice that there's nothing that looks like a multiply instruction here, because there's no multiply operation in the Little Man Computer instruction set. Instead, this program achieves multiplication by repeatedly adding a number to itself within a loop. I'll explain all of the operations in the Little Man Computer instruction set and how this program works in due course. But before we start writing programs, let me point out a couple of important concepts. Inside a real computer, program instructions have to be converted into binary ones and zeros before the computer can work with them. So each operation of an instruction set must have a number associated with it. These are the numeric values of the little man computer operations. You don't need to learn them in order to write code, but what you see in the simulator will make more sense if you're aware of their existence. Furthermore, when you work with little man computer code, you can declare and work with variables. This means you'll be referring to memory locations with symbolic names like num1, num2 and total. Before a program can run, these variable names have to be converted into numeric memory addresses, indeed binary numeric memory addresses. Fortunately, even a low-level language programmer is spared the effort of converting their code into binary. This task is performed by another program called an assembler. An assembler converts all of the code into binary and saves it as a single executable file. Now let's take a closer look at some assembly code. We'll start with something simple. This is the program I'm going to run in the simulator. The user is prompted to enter two numbers. It adds them together and outputs the result. Let's type up the program first. The program can be typed here. It's not case sensitive, but I like to use capital letters. I'm using three variables here, num1, num2 and result. I need to declare them. In other words, I need to reserve some memory. In Little Man Computer, you do that at the end of the program. While I was typing the code, I didn't concern myself too much with the layout. When I press the Submit button, this simulator takes care of everything for me. In fact, when I press the Submit button, a number of things have happened. My code has been converted into something closer to machine code. That's here. Notice that for every line of code I wrote, there's one line of machine code. Now in reality, the machine code would be all numeric. The input command, for example, is 901. The store command is the number 3. Something else that's happened is the code has been put into the RAM. In the simulator, I have the CPU here, and the RAM is over here. Notice that at memory location 0, I have 901. That's the input command. At memory location 1, I have the command 309. 3 means store, and 09 is the memory location where it's going to store the data. Memory location 9 is over here, and currently it contains 0. This piece of memory has been set aside. It's been reserved by the dat command. Memory location 3 also contains a store command. Remember, the store operation is the number 3. This store command says store something into memory location 10. Location 10 has been set aside. Memory location 4 contains a load command. The load command says load something from a memory location into the CPU's accumulator. In this case, load something from location number 9 into the accumulator. Here's the command in memory. The load operation is the number 5, and it's loading from location 9. It's worth spending a bit of time trying to identify each of these instructions from your program, and which memory locations, if any, they are working with. If I want to save my code, I can simply copy and paste this text into a text editor like Notepad. And then later I can use the load button to load it back into the simulator. Now, before I execute this program, notice that the program counter has the value 0 in it. The instruction register is currently empty. The address register is currently empty. And the accumulator contains 0. Let's press run. The input command has been fetched and is currently being executed, and I now have to type in some input. Notice that the program counter is now looking ahead at the next instruction to fetch. This is exactly what happens in the fetch-execute cycle. So let's type in a value. The number 5 went from the input box into the accumulator and was then stored in memory location 9. The instruction from memory location number 2 has been fetched, it's currently being executed, and I now need to input another value. Notice that the program counter is looking ahead at the next instruction to fetch. And when the program is complete, the output box contains my result, the number 12. If I want to run the program again, I can press Reset. All the registers inside the CPU have been reinitialized, but my program is still inside the RAM. There are some extra options here which can be useful. For example, I can clear the memory. Notice all the memory locations now contain zeros again. This button will reassemble my program into the RAM. I can also choose the speed at which I want to run my program, so I have default fast. Let's run it again. I'm being asked for some input, and immediately I'm being asked for another value to input. This time I didn't see the animation of things moving around inside the computer. You can also step through a program. Let's reset it again. I press on the step button. Input value loaded into the accumulator. Step again. Store value into RAM address 9. Step again. This is a very good way to get to know what's going on. I can see every step of the fetch-execute cycle taking place. The most important thing to realize about an assembly program is the role of the accumulator. When the input command executes, whatever the user types into the input box goes straight into the accumulator, overwriting whatever else is in the accumulator. The store command says take a copy of whatever's in the accumulator and write it into memory at the specified location. When the second input command here executes, whatever the user inputs goes into the accumulator, overwriting what was already there. In this program, the second number input is then copied from the accumulator into a location called num2. We then load the first number back into the accumulator. The accumulator contains num1. We then add the contents of num2 to whatever's in the accumulator. So immediately after the add command, the accumulator now contains the result we're after. A copy of this result is then taken from the accumulator and stored back into the RAM. The output command outputs whatever is in the accumulator, and then of course the program halts. Once you begin to understand the role of the accumulator, you'll find ways to optimize your code. For example, you may have already realized that you can perform the same task you've just seen with one variable. Here's a simpler version of the same program. When the first number is input, it goes into the accumulator. A copy of this is then stored in memory. When the second number is input, it overwrites the value in the accumulator, but it doesn't need to be stored in the memory. With the second number already in the accumulator, the add command adds the first number to it, overwriting the contents of the accumulator again with the result. The result is then output from the accumulator without being saved. Let's try something else. The purpose of this program is to prompt for a number, add the value 3 to it, and then output the result. Notice that you can't just say add 3. You have to declare a variable and assign a value to it with the dat operation. In Little Man Computer, the operand of the add operation must always be a memory location. In this case, the location we're referring to as 3. This is an addressing mode known as direct addressing. Some assembly languages will allow you to issue an instruction to add the value 3 to whatever's in the accumulator. If the operand is a data value, it's known as immediate addressing. Little Man Computer only allows for direct addressing. Let's give this program a try. This time I'm just going to copy and paste it into the simulator. By the way, if you don't see the same number of lines of assembled code as your source code, then it means that there's something wrong with the program. You've made some kind of syntactical error, which you'll need to fix. I'm going to run the program at full speed. I enter the number 9 and the output is 12. I've added 3 to it. Now let's see what happens if I attempt to use immediate addressing. I'm going to remove this variable and try to add the value 3. The simulator has happily assembled the code, but what's it going to do? I'm expecting an output of 7, but I'm getting an output of 906. Can you see what's happened here? The simulator has assumed that when I said add 3, I want to add the contents of memory location 3 to whatever's in the accumulator. You can see here that memory location 3 contains the out operation, and the out operation has the numeric value 902. So the simulator has added 902 to 4, giving me an output of 906. I'll say it again. Little Man Computer only supports direct addressing. If you want to add a value to the contents of the accumulator, you have to declare a variable with that value inside it. That is the program I need if I want to add 3 to whatever the user inputs. If you'd like to practice, here are some ideas for programs that you can try for yourself. Write a program to prompt for 5 numbers, add them together and output the result. So, for example, if you input 3, 4, 5, 6 and 7, the output would be 25. Write a program to prompt for 5 numbers, add the first 3 together, but subtract the 4th and 5th numbers. Then output the result. For example, if you input 3, 4, 5, 6 and 7, the output would be -1. Write a program to prompt for 3 numbers, add them together, double the total, and output the result. For example, if you input 3, 4 and 5, the output would be 24. Pause the video now to give them a try, and I'll show you some solutions in a moment. Here are some possible solutions. This program adds 5 numbers together. We have a variable called total, which is used to keep a running total of the numbers in memory while they are being input. Each time another number is input, it overwrites the value in the accumulator, but immediately after each input, the total in memory is added to the value in the accumulator, and the new total is stored back in the memory. This program is an excellent demonstration of the role of the accumulator. The total is being accumulated. Here's a solution to the second problem. Add the first 3 numbers together, but subtract the 4th and 5th. The program starts in the same way as the one you've just seen, adding the first 3 numbers to a running total in the memory. But when the 4th number is input, it is stored in a separate variable called next, so that the total can be loaded into the accumulator and the 4th number subtracted from it. The same happens when the 5th number is input. Once again, it's important to think about what's inside the accumulator after each line of code has executed. Here's a solution to the third problem. Add 3 numbers together and double the total. Again, very similar to the first solution, but with one final step. Add the total to itself. If you didn't come up with these solutions yourself, it's well worth coding them up in the simulator and stepping through the code. In the next video of this series, you'll see how to write branching code.